class, we are coming down to the end of the course. As you know, all work must be turned in by the 22nd, which is like next week. So in this lecture, there's going to be essentially the last topic or project that we have. I'm going to give you some information next on careers in electrical engineering. Also, I'll give you information on the project that you need to do. So I'm going to also post the last set of work that you have to do for the lab as well. I'll try to do it today in the time that we have left, so that you can go ahead and get that completed over this weekend. You can work on submitting this work, working on it so that by the 22nd, you have all your work completed, so that you're ready to take the exam in the next 2 days that follow. So today we're going to look at circuit analysis techniques, and these techniques include the branch current method, the loop current method. In essence, we are solving for circuits that have more than one power supply, and so we want to get the equivalent. We want to get the equivalent current in each branch, etc. So we'll look at some of these techniques. In solving the circuits, we need to use simultaneous equations sometimes, and so we'll be doing a quick review on simultaneous equations. So I will share my screen, and you go down to module number 9. Sorry, session number 7. Okay. In session 7, this is where we have chapter 9 that we're reviewing right now. And also there is a assignment there called homework number 6, which covers circuit analysis techniques. So I'm going to open chapter number 9. I already have it open here. So we'll start from there. Okay, so what are simultaneous equations? These are equations that describe the same system, so both of the equations are correct, and they describe the same system. And so to solve for the unknowns, we need to do some algebraic equations with this, and we have to use substitution to get rid of one of the unknowns and substitute it back into the equation so that we can solve for the unknowns. Again, there are a couple of ways to do that. One of the first ways is using the matrix, where we put the equation in a matrix form and we find the determinant. And this is one way we can find the unknowns. And the other way is by using substitution, where we substitute for one variable and we substitute it back into the equation to get the other unknown variable. Circuit analysis methods in chapter 9 require use of simultaneous equations. To simplify solving simultaneous equations, they are usually set up in standard form. Standard form for two equations with two unknowns is the following. So again, in standard form, you line up the variables. So if you have I1 or I2, you line them up. And of course, you also line up the answers and you line up the constants as well. So we put our equation in a standard form, and here we have an example. It says here, a circuit has the following equations. So as we continue, you will see that given a particular circuit, we need to be able to write those equations or extract those equations from the circuit. A circuit has the following equations. Set up the equations in standard form. So you can see here we have -10 plus 270 IA plus 1000 IA minus IB is equal to 0. And we have also 1000 IB minus IA plus 680 IB plus 6 is equal to 0. So when we rearrange the equations so that the coefficients are in order, we just expand everything and we calculate the total IA. So it's going to be 1000 plus 270 IA, and for IB it's going to be minus 1000 IB, and we put 10 on this side here because this is the result, right? Or this is the voltage that we're trying to find. Okay, again, how do we solve the simultaneous equations? Just a second. Right, again, you can use the algebraic substitution. We can use the determinant method, or you can also use a calculator as well. So some calculators allow you to put the equation in and it will solve the unknowns for you. Okay, so here's an example using substitution. So we are told to solve for IA using substitution. So how are we going to start? Well, what we do is we can solve for IB. So you notice here we put IB in terms of the rest of the equation. So we can say here that IB is going to be equal to 10. So IB is going to be equal to 1270 IA, right? Minus 10, and we will divide both, and we're going to divide this by 1000. So when we do that, we get 1.270 IA minus 0.001. That's for IB. So after we have obtained IB, we go ahead and we substitute it into the second equation. So we're going to replace IB right here. And so we have minus 1000 IA plus 1680. Instead of IB, we're going to put this expression right here. And this is what we did here. Is equal to minus 6. And so after we expand, of course, you can see that we have 1680 times 1.27 IA. And so that will be subtracted from, or we subtract 1000 from this. And then we have plus 1680 times minus 0.010 is equal to minus 6. So again, when we resolve this expression, we get that 1134 IA is equal to 10.8. And of course, we can find IA. We divide 10.8 by 1134, and we get that IA is equal to 9.53 milliamps. So when we will do our examples, most times you will see that instead of writing the current in amperes, we're going to write it in milliamps, just so that the equation can be simpler and we can have less errors. Instead of having a very small number, if we put it in milliamps, the number is more workable. So this is a substitution example, and we'll do an example very similar to that, so you can have some practice. It says, if you wanted to find IB in the previous example, you can substitute the results of IA into one of the original equations and solve for IB. So thus, we can take that 9.53 milliamps that we got, and we can substitute it back in one of the original equations, and we can find IB. Sometimes it's necessary to multiply an equation by a particular factor so that we can so that when we add the two equations together, we can get one of the variables to become 0. And you will see that as we continue. So this is one method. It's called the substitution method. And again, this is not new. You have done this in your algebra class. And so this is just a quick review. What about solving the simultaneous equation using determinants? So to do that, like I said, we need to express the coefficients. They must be in standard form, and then we will put them into a matrix. And then we can find the determinant of the matrix. And using that determinant, we can then go ahead and find the unknowns. So here is the matrix that we wrote. So 1207 minus 1000 minus 1000, 1680. Now to find the determinant of the matrix is going to be this coefficient times this coefficient minus this coefficient times this coefficient, and that's the matrix for us right here. Again, how do you solve simultaneous equations? So again, how do we find our unknown? So this is the characteristic determinant. This is what we get from our equation. If you want to solve for B, if we want to solve for the first variable, right, we are going to take the answers or the solutions. We are going to take the answers and we're going to move them into this first row here, and we're going to find the determinant. So we take the answers and we call the answers B. We move the answers into the first row, and then we find the determinant of the matrix. And we divide that determinant by the characteristic determinant, and that is our answer. Likewise, to solve for x2, we take the answers and we move it into the second row. Of course, this is the original one here. And we find the determinant and we divide it by the characteristic determinant. And we can do the same thing for a circuit with 2 variables and also one with 3 variables as well. So here is our example, right? So we have here our characteristic determinant here that we're going to find, and we move the answers 10 and minus 6 into the first row, and we're going to find the determinant of this, and we will divide it by the characteristic determinant, and that gives us our IA. Likewise, we move the answers to the second row, and in the first row we have the original values, and we find the determinant, we divide it by the characteristic determinant, that gives us the current IB. Okay, so many scientific calculators allow you to enter a set of equations and solve them automatically. The calculator method will depend on your particular calculator, but you will always write the equations in standard form first and then put the number of equations, coefficients, and constants. Pressing the solve key will show the values of the unknowns. So you can do it using the calculator. Okay, so this is just reviewing solving simultaneous equations. Like I said, we're going to do some examples just a bit. Then we have now we come to some of the methods that we use to solve for circuits or to analyze different circuits. Now, of course, this can be used to analyze basic circuits, but some of the more complex circuits are circuits with multiple sources that we cannot solve using just Ohm's law and Kirchhoff voltage law, but we need to apply a number of other techniques to solve them. So one of these techniques is called the branch current method. In the branch current method, you can solve for the currents in a circuit using simultaneous equations. Assign the current in each branch in an arbitrary direction. Show polarities according to the assigned directions. So again, first thing, we're going to assign some branch currents, and based on the currents, we are going to assign polarities to the resistors. And then we apply Kirchhoff voltage law in each closed loop, and we apply Kirchhoff's current law at nodes such that all branches are included. And then we solve the equations from steps 3 and 4. So what does this look like, right? So if you have a circuit like this here, we're given a circuit, and this circuit you can see it has 2 power supplies. It has one here supplying 10 volts and one here supplying 10 volts. Well, first step for us to do so, we're going to apply some branch currents. So we're saying, okay, the current in this branch is going this direction, right? As essentially it's coming from the battery, is going this direction. And we can also assume that the current from this power source is going in this direction. It's coming from the battery, and then we can assume that, hey, the current is going down here for this node, and it's going to come back to the battery on both sides. Based on that, then we assign the polarity. So where the current enters, we put a positive. So we have a positive here and a positive there. Okay, afterwards, then we're going to write the Kirchhoff's current, we're going to write the KVL for the Kirchhoff's voltage law equation for each branch. So again, here, it's going to be here. Now, these currents, we'll give them a name, right? For example, we can call this one I1, and we can call this one I2, and we can call this one I3, yeah? So if so starting here, we can say that, okay, if you're writing the Kirchhoff's voltage law, that Kirchhoff's voltage law says that the voltage drops here plus the voltage drop here should equal to the voltage drop there. So if you put all of these on the same side of the equation, it's going to be equal to 0. So we start here by saying, okay, now again, notice here, they're using K instead of ohms. So we have 0.270 K times I1, that's the voltage drop here, plus 1 times I2, which is the voltage drop here. The voltage drop is equal to the current times the resistance, is equal to minus 10. So again, this voltage drop plus this voltage drop will be equal to 10, right? So if you say minus 10, then it's going to be equal to 0. Likewise, for the for this branch, we can write that we can say for this branch that minus 1 I2 minus 0.68 I3 plus 6 is going to be equal to 0. Now you can also write it the same way here, right? You could have decided to write 0.68 I3. Yes, that's the voltage drop here. 0.68 I3 plus what? Plus 1 I2, correct? Minus 6 is equal to 0. So you can write it. So you can say that if you have a minus here and positive there, it equals to the same thing. If you have a negative here and a positive here, it's the same thing because both of them are going to equal to 0. But for this one, we just place the voltage drops as negative and the source as positive. The last equation we need is the Kirchhoff's current law equation, and based on our arrows, we see that the current in I2 is equal to the current in I1 plus the current in I3. And so this equation is there. And so we have gotten 3 simultaneous equations. Let's continue. So in the branch current method, of course, we have to write the equations in standard form. And because I3 is missing from this one, we put a 0 for it. And also because I1 is missing in this one, we put a 0 for it. And of course here, we just put the currents here. If the two currents add up to meet I2, if you add I2, so if you say I2 minus I1 plus I3, of course, you're going to get 0. So this is what we have expressed here. So this is the equation here. These are the 3 equations we have. Notice here we have now 3 variables. And so if we're solving, we need to solve using the substitution method or the determinant method or your calculator, and you can solve for the unknowns. So again, if you solve here, you'll find that I1 is equal to 9.5 milliamps, I2 is equal to 7.43 milliamps, I3 is equal to minus 0.21 milliamps. So what does it mean when you get a negative current? It just means that you assume the wrong direction. The negative results for I3 indicates that the actual current direction is opposite to the assumed direction. So that's all it means. So even though we get the negative current for our answer, that's fine. So this is one method. Again, you see the method, we use that method to do what? We use the method so that we can actually get the correct equations that represent the circuit. And when we get the equations, okay, our job is now to solve for the unknowns, right? Now we look at another method that we can use to get the equations for the circuit. This is called the loop current method. So again, this is another method we can use to obtain equations to describe our circuit. In the loop current method, we can solve the currents in a circuit using simultaneous equations. Now for this one is a little different than the branch current method because we are dealing with individual loops. Step 1 says assign a current in each non-redundant loop in an arbitrary direction. So we're just going to assign a loop current. Then it says show polarities according to the assigned direction of the current in each loop. Number 3 says apply Kirchhoff voltage law around each closed loop. And number 4 says solve the resulting equations for the loop currents. So let's look at an example here. So say you're given this circuit here and it has 2 sources, yeah? The same circuit that we had before. It has 2 sources. The first step is first to apply the loop current and set the direction of the loop current. We say, okay, the current is going this direction, it's going that direction. Based on the direction that we set, we need to put a polarity for the resistors. So of course, where the current enters the resistor is going to be positive. And after we have done this, we then are going to write the KVL, Kirchhoff voltage law equation, based on this loop current that we have. And so if you look at the equations here, the first one for loop A, we can say that we're going to have minus 10 volts. And so of course we need to, all the voltage drops are going to be positive so that we get 0 again. So we say minus 10 is plus 270 IA. And of course, since we call it loop A, we're going to call the current IA plus 1.0. Okay, so this is right here, 1.0 IA. Now, of course, since the other current is passing through it in the opposite direction, we're going to say 1.0 IA minus IB is equal to 0. So this is our Kirchhoff voltage law equation on this side. Now, our next equation, we start here. We can say we have 1.0 IB, so it's positive for B. IB minus IA because the other current is passing the opposite direction, plus 680 IB plus 6 is equal to 0. And again, keep in mind, for Kirchhoff voltage law, we are saying that the voltage drops are equal to the battery voltage. Yeah. So if you put them on the same side of the equation, they're going to equal to 0. It's the same as saying 5 plus 5 is equal to 10. Now, if we say 5 plus 5 minus 10 is going to be equal to 0. And that's what we are doing here. That's how we obtain these equations right there. Okay, so after we get the equations, what do we do? Of course, same thing. We are going to write the equations in standard form. And after we have them in standard form, guess what we do? We then solve the equations to obtain the unknowns. And of course, we said the different ways we can solve the equation. We can use substitution, or we can use the determinant method, or you can put it in your calculator to solve the equation. So one of the most important skills is using the methods to obtain the equations. All right, using the branch current method to obtain the simultaneous equations, or using the loop current method to obtain the simultaneous equations. And the second step, very important, is solving the simultaneous equations to obtain the unknown currents. That step is very important as well. So in this case here, you can see here that IA and IB were found. And after we found IA and IB, we need to find the currents I1, I2, and I3, because these are the currents that actually exist. So you can see here that the current flowing through here is going to be IA, so I1 is going to be equal to IA. You can also see that the current flowing through here is going to be IB, so I3 is going to be equal to IB. What about I2? Well, I2 is going to be IA minus IB, and so we have here is going to be 7.3 milliamps, so 9.53 minus 2.1. Again, keep in mind that because when we write the branch equations, since we put our resistance in K, whatever current we get is going to be in milliamps, right? Because normally for Ohm's law, resistance must be in ohms. But since we put the resistance in kilo ohms, the current is going to be divided by 1,000, so it's going to be in milliamps. Okay, loop current method applied to circuits with more than 2 loops. The loop current method can be applied to more complicated circuits such as the Wheatstone bridge. The steps are the same as previously shown. The advantage to the loop current method for Wheatstone bridge is that it has only 3 unknowns. So again, we can apply the loop current method to more complex circuits. So again, the question says, write the loop current equation for loop A of the Wheatstone bridge. So if you look at here, we have a Wheatstone bridge with 4 resistors and a resistor right here. And we are told to write the loop current method for loop A. So again, if you look at this here, the equation is going to be, we start with minus 15 plus 0.68, and we're asking, okay, what current is going to flow here? Okay, the current is going to be IA, and since the current is in the opposite direction, it's going to be minus IB. Then we look at this equation as well, plus 0.68 IA minus IC is equal to 0. So this is the loop equation. If you're told to write the equation here, of course, it's going to be equal to we're going to have 0.68 IB minus IA plus 0.68 IB, and then of course this one as well, plus 0.50 IC is equal to 0. Likewise for this one as well. So again, after we obtain all the loop equations, then we can solve them simultaneously. But the point of this course is just so that we become familiar with the techniques and we are able to use them to solve some simple problems. Of course, there are more complex problems that we'll not be able to handle in this course, but we want to be able to use the techniques. And what techniques are these? like I mentioned to you, we talked about the substitution method some time ago, so I'll reintroduce it. So if you have a circuit with more than one source, we want to be able to use substitution to solve that circuit. We want to be able to use the branch current method to solve the unknowns. We also want to be able to use the loop current method to solve the unknowns as well. Another technique that we can use is called nodal analysis. And essentially what you do in this technique is that you determine a number of nodes, and then you select a node as a reference, and then you assign voltage destinations to each unknown node. You assign currents into each node except for the reference node, and then you apply Kirchhoff's current law. So here's an example. So if you have a circuit like this, you can say that, hey, this point is point A, and I'm saying that the voltage at this point is point A. So I can call this voltage here VA. And so you write the Kirchhoff's current law based on this. You see, you apply the current directions. So you can say that I1 plus I3 is going to be equal to I2. And of course, you can write all the currents in terms of this reference. So you can say that, okay, what is the current of what's the current of I2? Sorry, I1 is going to be, okay, the voltage source minus the voltage drop. Sorry, the voltage drop. So again, if you ask the current here, we can say, okay, it's the voltage in this resistor minus the resistance of that resistor. And so what is the voltage here? It's going to be Vs minus Va. All right, so that's the that tells us the voltage that was dropped here. So it's going to be Vs minus V over R1. Likewise for R2. What is the voltage here? It's going to be whatever voltage is here, Va divided by R2. And likewise for I3, we can say that it's going to be Vs2. So this source here minus the voltage here divided by R3 will give us our I3. And after we have done this here, of course, we are going to substitute to find our answer. So we can say that, okay, based on our Kirchhoff's current law equation, I1 plus I2 is equal to I3. We can then rearrange it. And of course, we put our I2 on this side here. And now we substitute the resistances in here, right? After this, you see now we are then going to solve for VA, right? We can find the common denominator for this, and then we can solve for VA. And after we find VA, of course, we simply substitute, and we can find our current. So if we know VA, we can substitute VA into this equation here, and we can find I1, we can find I2, we can also find I3. So we're going to do an example of each of these, and this is what we want you to, here we have some quiz questions here about simultaneous equations. All right, so let's go and look at some of the examples that we have for you. All right, so in module number session 7, let's go ahead and look at the handout. So there's homework number 6, circuit analysis techniques. Let's open that homework, and there is a handout inside here. Homework 6 handout, and let's open this handout. Now we should have some examples of each that we can proceed with. All right, so let's start from the top in this handout. Again, this is the homework number 6 handout. So we have example 1. So again, notice this is just like the equations that we have here, but instead of having just 3 resistors, they have an extra resistor on the bottom, right? So how do we solve this? If we use the branch current method, so what are the steps? The first step is to set the direction of the current. The second step is to write the branch equations. The third step is to set polarities based on this current, right? So again, you can see here, we set the direction, and of course we say that where the current is entering, is going to be positive. So the current is entering there is positive, current is entering there is positive, and so forth. Then we write the equation. So we start on this side. We say 6I1 plus 10I2 plus 4I1, because again, I1 goes there, it adds with this one to form I2, and it's going to split back into I1 here. So plus 4I1 minus 90 is equal to 0. You can write the equation for this one as well. It's going to be 15I3 plus 10I2 plus 5I3 is equal to 40. Now keep in mind, we did not convert the resistance into kilo ohms, so our answer is going to be in amperes. Then we write the KCL, the Kirchhoff's current law equation, that just says that I1 plus I2 is equal to I3. So we say that I1 plus I2 minus I3 is going to equal to 0. And so the next step is, of course, is to write the equations in standard form. Yeah. So in standard form, of course, we're going to have 10I1 plus 10I2. Of course, 6I1 plus 4I1 is going to be 10I1. 10I1 plus 10I2 is equal to 90. Then next equation we have here 0I1 plus 10I2 plus 20I3 is equal to 40. And we have the KCL that says I1 minus I2 plus I3 is equal to 0. Okay, so the next step now is to solve the simultaneous equation. So the first step is to obtain the equations, and the second step is to solve the equations. So you can see here that I have these three simultaneous equations that I need to solve to find I1, I2, I3. So here I'm just going to solve them using the determinant method. So again, here you can see here this is the matrix that I wrote, right? And I need to find the determinant. So how do you find the determinant of this matrix? Of course, it's going to be this branch here, 10 by 10 by 1 minus what? 1 by 10 by 0. Yeah, that's how we find the determinant. Okay, so I found the determinant to be 10 by 10 by 1 is going to be 100. Yeah. Now to find the unknowns, like I mentioned to you, we need to move the answers into the first row. But with the 3x3 matrix, we also need to have two other rows outside. So we're going to have the first row and the second row outside again. So that's why we have, you can see here, we move the answer into the first row and everything is the same. And we put the first and second row here. So notice the answer is still there. So if you look here, what is the determinant of this matrix? We have 90 by 10 by 1. And of course, the way you do this, the way you solve this, you need to find the determinant here, or the 90 by 10 by 1 plus 10 by 20 by 0 plus 0 times 40 by negative 1 minus what? Minus 0 times 10 by. So again, you multiply this, you add it with this, you add it with this, and you subtract it from what? Subtract it from this plus this plus this. And so in my answer here, I have 90 plus 0 plus 0. And of course, I'm going to minus it from this guy here. So the only one I have here, so again, I'm minusing it from a negative, subtract the negative will give you a positive. That's why I have positive 180 here, which is 20 by 90. And then I'm going to minus now 40 by 10, which is 400. So the solution here is 2300. When I divide it by the determinant, I'm going to get I have a current here of 4.6 amperes. Okay, I need to also revisit this because 10 by 10 by 1 gives us 100. And so the determinant of this matrix should be 100. And for some reason, I'm using 500 here. So I have to look into this. But this is the current that we get. And then after you do it for I1, of course, you do it for I2. The only thing you are changing, you are moving the answers into the next column. And of course, here it's going to be in the next column here as well. You find the determinant and you divide it by the characteristic determinant. And then you move on to the next one and you solve it as well. Anytime you have a negative current, you're saying that the proposed direction is wrong. And that's for the branch current method. Let's have another example here, example 2. This looks at the loop current method. So you can see here that we have a circuit and we're going to apply some current directions. So I say IA is going this way, IB is going this way. And based on that, we're going to write some KVL equations for each branch. So of course here, keep in mind that based on the direction, we need to put the polarity for the resistors. But of course, the battery polarity is going to stay the same. So I'm going to have here 5IA. See here. So if I start up here, 5IA plus 10IB. Now, since the direction is opposite here, it's going to be plus 10IA minus IB. And here we're going to have plus 10 because it's in the opposite direction, plus 10. That's for the battery, minus 15, which is our source right here. And of course, if you write this in standard form, we're going to have here 15IA minus 10IB minus 5. So we just put the 5 on the other side. What about this branch here? We also write the mesh current equation for this branch. So if we start here with we have the 10, we're going to start here. We have 10 IB minus IA because the current is in the opposite direction to this one. Then we have plus 6 IB plus 4 IB minus 10 because this is our only source is equal to 0. So we put this in standard form. We're going to have 20 IB minus 10 IA. And then, of course, we have two equations to solve, and we can solve the simultaneous equations. In this case here, we're deciding to solve them using substitution. And so these are our two equations that we have right here. What we're going to do, we want to eliminate one of these variables, right? So we can substitute it back. And the easy way to do that, we multiply equation 1 by 2. So if we multiply this equation by 2, multiply this equation by 2. Of course, keep in mind we have 10 IB here and 20 IB. So we're going to then have 30 IA minus 20 IB. And then we're going to add it to this equation where we have minus 10 IA plus 20 IB. And so our answer is going to be 20 IA is equal to 20. And so we can find that IA is equal to 1 ampere. Then we substitute IA back into equation 1. And so now we have 15 IA, so 15 times 1 minus 10 IB, so we get that IB is equal to 1 as well. And now to resolve the currents, of course we know that IA is equal to I1 and IB is equal to I3, and I2 is going to be equal to I1 minus I2. So I2 is going to be equal to 0. Again, keep in mind that I2 is equal to I1 minus I3. And the reason this is so is because of the direction of our currents here. So the currents are not adding to form I3, but they are subtracting, all right? That is why we have that I2 is equal to I1 minus I3. Let's look at another example. So again, you can, this is a good time for you to use simulation to verify your answers, to ensure that you are getting the correct values. So you can design a circuit in the multi-sim simulation tool that you have, and you can actually have multiple sources, and you can then measure the current and the voltage. And what you will get is that you actually get the equivalent current and voltage based on both of the sources. So the examples that I give you to solve you can put them in multi-sim to get the answers. But the analysis techniques that I show you, they show you use them to show how you get your answers. So the simulation allows you to check if your answers are correct, but you need to use the analysis to know, okay, how do I solve this? How do I get this answer? So of course here you can see here the current flowing in this direction is 6.4 milliamps. Current going here is 1.43 milliamps, and the current there is 7.86 milliamps. So I'm going to show you how you can, maybe we can do a simulation example. So you can see that the same circuit that I simulated here, I'm using analysis to calculate, to find the currents. So we start with the branch current method. So first again, we assign the directions, then we write the equations, and then we write the branch equations. So again here, I'm going to have here 1I1 plus 2.2I2 minus 11 will be equal to 0. On this side, I'm going to write, we have 2.2I3 plus 2.2I2 plus 11 is equal to 0. And so again, and then the currents, I write the current, I1 plus I3 is equal to I2. Put them in standard form, get the matrix, and then the next step is, okay, how do I solve the matrix to get the current? And you can see here, solving the determinants to find the current. This is the primary determinant. And again, if you notice here, for the primary determinant, we also need to put the first and second columns here to obtain this primary determinant. So this is what I missed in the last problem. So after we have the primary determinant, then we move the answer to the first column to find the I1, and we move the answer to the second column to find I2. Of course, if you move it to the first column here, it needs to be in the first column on this side as well. And for I3, of course, we have the first and second column, and of course, you see that we found the currents, but the only thing, we had a negative here, and that tells us that our I2 was in the wrong direction. So I2 should be going up instead of down. Where is it? Told us that our current for I2 was in the wrong direction. Negative for I2 and a negative for I3, and that tells me that our current is going in the opposite direction. The next problem we have is nodal analysis. So we have an example here of solving this kind of problem using nodal analysis. Like we said, the first step is to appoint a point VA. Let's call VA the reference here, and we're going to assign some currents. Of course, it's very easy to say that I1 plus I2 is equal to I3. And then you write I1, I2, and I3 in terms of the reference of VA. After you have done this, you're going to find you replace the resistors here. You find a common denominator for all of them. And then after you find a common denominator for all of them, you then solve for VA. When you solve for VA, you go back and substitute that same value for I1, I2, and I3. And you can find the currents. So this is a very simple method as well in terms of resolving these kinds of circuits. But the point is not just getting the answer. The point of our study is so that you can know the techniques, you know the steps to follow, and that you can demonstrate that you can use the techniques as well. So here's an example here. We have that's a typical example. You can see the currents obtained from simulation and where the direction of the currents as well. And here we are going to solve it using the branch current method. Same thing, we assign branch directions, then we write the branch equations based on the polarities, and then we obtain the simultaneous equations. We find the determinant, which is minus 144, and then we substitute the answers in the first column. we find the first current 9 amperes, the second current 4 amperes, and the third current, which is 5 amperes. So again, we got, based on our assumption, we got I2 wrong. We said I2 was going down, and our calculation tells us that it's not going down, but it's going up. Okay, and that is the last example. So I want you to take a look at these. Let's go back and look at the homework. See what the homework is like. Let's go and download this. I don't think the homework is that difficult, but it asks you to use all the techniques. So what are these techniques? It says, please solve example 1. So you're given how many problems? 5 problems, right? And I'm actually telling you what I want you to use. So again, with the answers, you can get the answers using simulation. You can simulate the circuit using multi-sim like I showed you. And you have to use for the lab, you can use the simulation tool to get the different currents that you need to solve. But that's fine. I want you to show the working. And the working, when you show the working, you need to show me something like that, that you are able to solve the problem. So again, number 1 says, solve example 1 using nodal analysis. Solve example 2 using branch current method. So you're only going to use the technique to solve that example. Please solve example 4 using nodal analysis. I think this should be example 3. And solve example 4 using the mesh loop current, and example 5 using the mesh loop current analysis method. So what are the problems? Oh, Rasta. Okay, so the problems, the problems that I'm asking you to solve, I did not include them there, but these are the same problems in the handout. So let's look at the handout one more time. So in the handout, notice we have example 1, correct? Then we have example 2, example 3, example 5, example 3, and then we have example 4. So we have 4 problems in the handout. And for the homework, I'm telling you, okay, I already give you these examples, and I'm asking you to, so I already solved them using a particular method, correct? I'm asking you to solve the same examples using a different method. And what is the method that I want you to use? I stated it here. So do you have any questions as to what the homework is asking you to do? So it's asking you to solve the examples in the handout using the particular method that I'm asking you to do. Questions about what the assignment is asking you to do. So it's asking you to solve the examples that I already gave you in the handout, but I'm asking you to solve them using a different technique. Any questions for me about that? Questions about that? No. Okay, so this is the last lecture part. I still have to give you some information about the project that I want you to work on. It's a programming project. Of course, you will get bonus points for completing it. And I have something small for you about careers in electrical engineering. So go ahead and work on that. If you have any questions, feel free to contact me. There are lots of tutorials online as well, but I think I try to make it very clear and plain what you should do. Again, these techniques are not hard. It's a procedure you follow to solve these kinds of problems. And again, these problems are problems where you have multiple sources. And notice I didn't try to make it difficult by adding current sources and voltage sources so that you would have to maybe work on it harder. We only use voltage sources, and we just want to apply the techniques to obtain the answers. So the point is not about just getting the answers, it's about, can I use the technique? And I gave you a couple of examples that you can follow.